Okay, so let's go for the last lecture for today. I will talk about inverse modeling of EEG and MEG data. So, short outline, I just give a quick introduction which summarizes a little bit what happened already and what's going to happen. Then I will talk about inverse modeling and specific methods there, and then a summary, which basically is a bit of summary of all what we did today. So first I want to show you a little video. Hopefully it's working. So what you see here now is an elephant fish. This elephant fish lives in the Nile, and I think you know the Nile is a muddy river, so it cannot see a lot. But this fish has developed a technique to, that's normal, it's a beeping sound, so this fish emits electrical current into the water, to basically get an overview of how it works. It also has an organ to receive it. What we did there, it's like a video from 15 years ago, my supervisor put one of these fish into a water tank, stick a lot of EEG electrodes into the water tank, and just recorded EEG of the water tank, the fish. So, if we also continue, we can make this in the video, it is weird. Like, I think this machine was back then 15 years old, so we talk about EEGs, so which is 30 years old. But, just leave it. It's a really old machine. We will later see the idea of this is basically source reconstruction. So what we can do is now we have an EEG, we have a water tank, which is our forward model or our robot conductor, and then we can just localize the position of the fish in the water. That's what you are currently doing now. Try to localize the source in the brain, but you can look through the brain like a water tank, and there's more source than just one fish. So this is a very, very simplified version of the source reconstruction. Also, this very, very old computer you see over there, there's a nice reconstruction of the fish, like it's really real-time imaging. So also back then, possible. So maybe sometimes we get a closer look to that, updates all the time, like you can already see it nicely, the fish is very nicely localized. Basically doing a single type of fish, nothing more. Okay, yeah, now you can see it, it's a fish moving around, I've updated the source reconstruction. Okay, why did I show you this video? That's what we're going to do, source reconstruction. So a little bit of how to model a source in the brain. So what we see here, what we always see today in the morning is the pyramidal tracks of the neurons we see here. Basically, when these tracks we see some signal, we basically have some activity in this direction when it's firing. That's what we would try to model. So basically first we start off with this part here, these tracks. There are a lot of sources, and the black arrows is everyone is a source. Then we sum it up to one white one, which basically is a dipole. Then we take a bigger look at all these clusters and summarize them again. Then you can already see, basically we have a lot of neurons active, and we sum up to one activity. And if we now look at the white one, because our brain is not just a flat surface, we also have a little bit of curvature, so the dipole is more or less moving around, so we have also a moment to consider. Okay, the inverse methods we'll talk about. First we go for single and multiple dipole models, where basically just a single patch or a few patches of cortical activity is measured. We look for a distributed source model, where we see basically activity all over the brain and look where it's the strongest. And then we talk about spatial filtering, more famously known as beamforming, where we look at different sources that are uncorrelated to each other and to the noise. So let's go for single and multiple dipole fitting. I think you all know parameter estimation. I think everybody of you have done at one point in your studies a linear regression. If not, shame on you. Normally we have like an independent variable x that we measure, and then we try to conclude on a dependent variable y. That's basically parameter estimation. If you look now at the model of that, like f would be a model, which has parameters a, b, c, and whatever, which we can choose. And then we try to reconstruct the idea about y, how it's dependent on x. That's what we're doing with the dipole parameters. Which parameters we can look for? We can look for position, the orientation, the strength. What we try to do is we try to model it so that the model minimizes the difference that the model says to the real data. So that would be an optimal model. Basically, a regression line for parameter estimation, normal parameter estimation. Okay, good thing about sources is they're linear, these signals. So if you have like several active activities in the brain, we can just sum them up. But also it allows us to disentangle dipoles because they're linear, so it's easy to distinguish them. So easy, depending on the parameter. To give it more content, let's think about a dipole Q. A dipole Q has basically three orientation. It has an X orientation, a Y, and a Z. So basically we can separate one dipole into three directions and estimate that. To put it in the equation, basically our signal Y depends on the G. It's a forward model, Marikala explained well, and we multiply the forward model just with the sources. So basically we have an equation, Y equals G times Q. What are we interested in? Q. How do we get that? You remember? Maybe norm estimate, just invert it. So Q is the forward model inverted times Y. And then we already have, in this case, the directions of the source, the moment. To make it more ugly, let's say, we now have an error term, which is basically our model, minus the real data. So what we want to see is like, how close does it get? It's like far away, or it's another way. So basically we plot the parameters we choose in our model and plot it to the error that we get. So basically the difference between real data and model data. What we here want to get is to the green point, because the green point is the lowest error. So this is where data is mostly explained. Oh, you see like, oh, there's this error valley. Oh, why not just go for the green one? Because what we only know is this. We don't know the valley. We just know 2 error points, and now we have to find the real minimum. And that's what we're going to do now. So first we start with a grid search. Basically, we look in the brain for predefined points and just compute them. For example, we can go from medial to lateral, one possible locations, and next direction inferior to superior, times 100, so we have 10,000 positions. And if we have odd dimension, for example, we could have 1 million positions. Let's assume every computation we do at every position takes 1 milliseconds. So if we want to do this now, it would take 16 minutes. That's fine, we can do that. Now we're looking for 2 sources. So basically we have this times squared, so we have 10 to the power of 12. And if now every computation takes 1 millisecond, we have to wait for 32 years. That's not good. So what we then do is we basically do a very coarse grid search, as you see here. These black dots, for everyone we can compute it, and let's assume we ended up with the red point. We know, oh, red is not the perfect point because we want to have the grid green. How do we get there? The gradient descent, that's what we can do. Everybody heard of the gradient descent already? Well, looks a little bit, maybe. Okay, the idea is very easy. Just assume we are in a hilly region, but it's very, very foggy, so we can just see the steps behind it. Then we look around, want to get to the valley, there it's steeper, then we make a step. Then we look around again, where it's steep, and basically you follow step by step along the steepest direction until you are very low and can't go any lower. So basically it's just walking down until we reach a very low point. Okay, and then we would have, going from this topography we started with, apply all these methods, dipole fit, and then we have it. This model, you need that, you already computed that in the forward part, and now in the hands-on you will basically use the methods to reconstruct these sources. Okay, to sum it a little bit up about the strategies, if you assume we have just one dipole, the first thing we do is scan the brain, look for the best explaining point, and then just do some gradient descent to optimize it still. What did I do? Oh, yeah, thank you. 2 dipoles, there's one way you can just say, let's assume we have a symmetric pair, then you, let's say, scan half the brain, and then take the other one and do it again. And then you can have also dipoles. If you have 2 or more, you can also do a sequential dipole fitting. What is that? I will show you now. So let's assume we have more than one active dipole at the same time. For example, we have a radial one, a tangential one, oblique one, or whatever you can think of, several dipoles at the same time. So I just look at the Bezier manual, and it says like, look at one example. We have like this red source activity and the blue source activity. And if you look up there to the activity, it's a little bit time shifted. So there's a difference between them in time. But if you just overlay in the topography, it's not clearly visible here that there are 2 sources underlying. And if you look at the topographies over time, it looks like a rotating dipole. So how do we deal with that? So we first do is we just put one source at this position, compute the Homlle model, do all the forward modeling, see the waveform, and see how this waveform explains our data. In this case, we see, yeah, it's getting better, but there's still something in the data, so not everything is explained. Next step is we leave this dipole in there, put another one, do the forward modeling again, look at both topographies, and then we see, the data is well explained, so there's nothing left in the data to explain for. So basically, and if there would be still something, you would for the third point, fourth, and so on. Okay, distributed source model. What's a distributed source model? Here we don't actually estimate positions because we have positions which is like the whole brain. So we use a predefined grid and estimate the source strength. It sounds in principle very easy to solve, but we have way, way, way more unknowns than measurements. That's a problem because then there's an infinite amount of solution which explains our data. That's quite a lot, so we have to get a little bit less than infinity. So we have to add additional constraints to get less possible solutions. And then again, we have a linear estimation problem here. So this could be a distributed source model, like it's a cortical sheet. If we let it closer, you can see these arrows. So basically every arrow here represents one source of the brain. And again, we go for this linear estimation problem. Looks similar as we had before, but now we have a lot more unknowns at Q. But basically we do the same one, we just invert it. But if we do it, we have an infinite amount of solution to do that. So we have to go for regularization. So basically the model is we have forward model times the source, which explains our data, and we have some noise in there. And that's what we normally want to minimize. The model has to explain the data best. Regularization means we have this additional term with this lambda. I think we heard some fMRI people were already there, so they quite know about regularization. It's this weird parameter, you always have to choose lambda, and then the data gets better or not. It's a little bit of magic sometimes. But in this case, it's quite easy to understand. So the first part really says, our model, how does it explain to the data we measured? And the other term is like we add additional prior, for example, the covariance matrix, and say if our source really lets something explode, it has to be penalized. This is how lambda we choose. So it's like a trade-off parameter. You can choose lambda very low, so it doesn't matter too much about this other term, but very high, so you care a lot about the other parameter you specified. And if you all do this, you can have a minimum estimation. In this case, it's quite a focal one, and this would be the source you would reconstruct. Okay. A little bit about beamforming methods. I think everybody heard of beamforming before. It's like fine and good thing. We are not estimating position per se again, but what we do is we manipulate filters at the source level, which try to explain the data we have in there with some assumptions. So let's go for how to do it. So we have a wet source in the brain, like we have activity Q at location R, and this produces with some lead fields our data Y that we measure at the EEG or the MEG. What we want to do now is we want to estimate Q by a spatial filter. So it means we multiply the measure data with some weights. And then we sum it up, and then basically we have at the source our topography. Basically we go from sensor level to a source level where we would estimate a so-called virtual channel. So the ingredients again, we have a source Q, which we multiply with a forward model, and there would we end up with our measurements. So to rehearse a little bit, everything that's written that has already said. So basically we look at this G and Q again, which was Y we said, but also Y has to be the source we want to estimate times the weight. So if we now basically do a little bit of basic mathematics, don't be afraid. We take this matrix, which is equal Y, and put it here. So we have W times G times Q is the source we want to estimate. So this part can be normalized, so we divide it by Q, so everything has to be 1. So basically the weights times the forward model has to be equal 1 at our source we want to estimate. So let's say we want to look at this purple one, so this filter we computed with the forward model equals 1, like here. Then we have another source with the blue one, which is equals 1 here. But now comes the crucial thing. If we take the filter from the purple source and apply it to the forward model of the blue one, it should be 0, because that's the assumption that our source is independent, which means the filter we apply to a different source should be 0. So if we also take another point, has to be 0, this has to be 0. So basically the first part means the W times G is our unit gain constraint, that has to be 1. And then all other position has to be 0, which in practice is of course unfeasible because you always have something there. So what we say is now we just want to minimize the variance at that position. So it has to be not 0, but close to 0, as close as possible. Okay. To sum up what we already did, so Marie-Carla was talking about the forward modeling. Forward modeling is required to go from topographies to the source level. So basically the problem with EEG and MEG that Sophie said is that we lack spatial resolution. So what we then did is like we create a forward model which actually explains our geometry so we can include the spatial resolution. So basically combining the time accuracy of EEG and MEG and put it together with the spatial accuracy of an MRI to get to the source modeling. So we also talked today now about the inverse modeling to estimate some source parameters with different assumptions, how we model the source as a single dipole, as a distributed source, or as beam forming. Today, I think we mostly talked about the where about the source, or you will see that. I think also I talked to some people about the what and when, like time thing was not mentioned, really when and which frequency space and the power. So we have like not talked about time course of activity, we didn't talk about spatial characteristics and so on. So this is just a snapshot, let's say an easy one we talked about, but all the other parts can also be applied in more sophisticated and advanced, let's say, which was not coverable in, let's say, 1 day, but when we do a Nijmegen this kind of workshop, we have like 4 days, and this would also be covered then. Yeah, so basically in the end, we're looking just for an elephant fish and the Nile, but our map is not perfect, so that's our forward model we created. Some parts are missing, we're not sure about that, but we try to make this map better and better, and then we do source reconstruction, and roughly our elephant fish has to be there. Yeah, that's it. Thank you very much. Now it's time for questions.